We can start, please, Vladimir.
So thank you, Mr. Chairman, and I also would like to thank the organizer committee for introduction. It's a great pleasure to be here and participate in scientific discussions and also have some time for art and skiing. So a very nice combination. And my talk will be devoted to different regimes of exciton transport in two-dimensional semiconductors. So a little bit later, I will show which semiconductors we consider. We'll discuss most interesting regimes which we try to study in. And here is the plan of the talk. You can see that this diagram, I will comment it a little bit later, but this diagram directly demonstrates the plan. So there will be some brief introduction concerning excitons and the ways of exciton transport measurements. Then I will discuss some peculiarities of diffusive transport. Then I will spend some time discussing hydrodynamic regime. And if we have enough time, anyway, I will try to spend a couple of minutes describing the possibilities of the superfluid regime analysis. So let me start from my colleagues who strongly helped us to obtain the results. Here are these three colleagues, Vladimir Palulin, Alexander Kolerovich, and Alexei Chechkin. They correspond strongly to the diffusive model, and in collaboration with Mikhail Glazov, we studied the hydrodynamic regime of exciton transport. So let me briefly start from the history of the exciton invention and what is exciton. So today in the morning, during the lecture by Alexander Chanov, there was the word exciton in his presentation, but what is it? Maybe not all of you know. The light absorption in semiconductor leads to the excitation of electron from the valence band to the conduction band, and then due to the presence of strong Coulomb interaction between electron in the conduction band and hole in the valence band, the exciton is formed. This is a quasi-particle, and the first one who introduced exciton, who understand the concept of exciton, who understood that such quasi-particles could exist in solid states, was Yakov Frankel. His paper was published nearly 100 years ago in 1930, and he was interested in the transformation of light into heat in solids, and he understood that when the light is absorbed and you have the electric field applied to the semiconductor, it could be a situation that there is no photocurrent. This means that electron and hole are bound and there is no photocurrent, but he called this a quasi-particle exciton, and the idea was that he analyzed the problem in the tight binding model, how it is called right now, and then he understood only that wave functions of electron and hole are well localized at the sides of the lattice. And these are so-called Frankel excitons, or excitons of small radius. 8 years later, there were two papers by Gregory Vanier and Sir Neville Mott. They analyzed the same problem, but in the approximation of effective mass, and the 1 year mode exciton or large radius exciton were introduced. And as excitons are hydrogen-like quasi-particles, in the three-dimensional case, we can use expression for hydrogen energy and Bohr radius, but we should consider the effective mass and the presence of the electrical permittivity. Then it is possible to get an expression for exciton series. This works quite good in three-dimensional situation. In two-dimensional case, everything will be more complicated. And here also I would like to show you the first observation of the excitonic lines, exciton series, which were obtained by Gross and Karif, also in Ioffe Institute, and Frankel was from Ioffe Institute, so the concept of exciton was born in the Soviet Union, in Leningrad and St. Petersburg right now. So the problem is that the binding energies in three-dimensional case are quite small. So it is not easy to observe excitons at room temperature, and everything changed when two-dimensional materials were invented. And today in the morning, we saw how it is possible to form different heterostructures from two-dimensional structures. And the most intensively studied 2D materials when we are speaking about excitons are these three materials. These are semiconductor nanoplatelets, transition metal dichalcogenase, mostly transition metal dichalcogenase, and also layered perovskites. All of them have their pluses and minuses, but in all of them it is possible to observe excitons both at low temperature and at room temperature. And what is important that excitons not only determine optoelectronic properties of the material, but they can also move around the whole area of material, performing the energy transfer in such materials. So it is quite important to understand to understand the model, how it would happen. Here you can see experimental results which clearly demonstrate that excitons are present in nanoplatelets, in layered perovskites, and also in different transition metal dichalcogenides. And transition metal dichalcogenides could be encapsulated using hexagonal boron nitride. In this case, the lines are very narrow, but even without boron nitride, at low temperatures, you can see well-resolved peaks in photoluminescence. There are different regimes of exciton propagation, and here is the picture from the book by Alexei Chernikov and Mikhail Glazov. The most widely studied and the most interesting regimes are shown here. So these are hopping regime, the regime of weak localization, semi-classical regime, and also the regime when the collective movement of excitons is present. This is so-called hydrodynamic. So in my talk, I will pay special attention to the diffusion and the hydrodynamic transport of excitons. And the question is how to analyze the transport properties, because excitons are bosons, their charge is equal to 0, and we can't do something like we do if we are analyzing, for example, the mobility of electrons or holes, when we can apply electric field and know quite everything, analyzing the transport properties. But excitons are optically active, and the main idea is shown here. So if we have a two-dimensional structure, transition metal dichalcogenide in this case, we should optically create local exciton population. And then it starts to spread with time. So we should have the possibility to analyze the exciton density as a function of distance from this place where exciton population was excited and time. So we need time resolved and special resolved photoluminescence. Then we can analyze the changing of the profile of the photoluminescent signal. It will spread, and as it is proposed by the experimentalists, those who are measuring, in the linear regime, we can fit this signal by the Gaussian, because Gaussian function is the solution of the linear diffusion equation. But the life is more complicated. The linear regime is the simplest one, but not the only one. So what we see if we analyze experimental results, this is a typical experimental, this one, the left panel, the typical photoluminescence spectrum with spatial and time resolution. And you can see that if you measure such as photoluminescence, there is no spreading at all. It seems that you create excitons and then they start to recombine, and there you can see really nothing. But what is important, you should remember that excitons have a finite lifetime. If you normalize this signal by the maximum value, you will see that some spreading of the exciton cloud is present in the system. What will be interesting for me and what I will focus on is the situation like this, shown on the left panel, when there is some spreading and then the exciton population becomes narrow. So it seems that some kind of effective negative diffusivity appears in the system. And I will discuss the possible origin for this phenomena. So what is important is that excitons transport is not very simple. It's not spreading without any problems, if it's possible to say so, because you always have a disorder, you have phonons, you have some traps in the structure. Moreover, you have other excitons. So you should consider the presence of scattering at the static disorder and the possibility of excitons trapping. You should consider scattering on phonons. This is one of the main mechanisms of scattering in low temperatures, long-wave acoustic phonons. Then there are another charge carriers. So, for example, if you have exciton, and for example, in addition to exciton, you have electrons and hole, positive or negatively charged excitons could appear. They are so-called trions, and there are also other excitons. So, exciton-exciton interaction gives nonlinearity to the problem, and the solution becomes more complicated. So, briefly speaking, I would like to show some most important moments concerning the Hopping regime, semi-classical regime, and some interference effects. Hopping regime is realized when there is some disorder potential, and it is well known that there is an exponential dependence of diffusion coefficient on temperature, and the Hopping transport is rather complicated and rather slow, so it's very difficult to observe it experimentally. There are only several papers devoted to this problem, and it is not very clear is the Hopping regime or not, but nice physics in Hopping regime, but the problem is that for Hopping regime, not for us, that van der Waals heterostructures, transition metal dehalogenized, which are encapsulated in boron nitride, they could be very clear. So you can have the situation when there are no disorder potential, which could lead to the localization and further hopping with the increasing of temperature. Semi-classical regime is most widely studied, both experimentally and theoretically, and there are different scattering mechanisms. Two main mechanisms are scattering on static defects and also scattering on phonons. And sometimes semi-classical regime is not enough, so you have to consider some quantum to solve some quantum problem. And the most important moment here is that some self-intersecting trajectories could appear, so the constructive interference could lead to the weak localization, and it leads to the decreasing of the diffusion coefficient. Such experiments were performed, and this decreasing caused by the presence of such closed loops in the exciton trajectories were observed. So all these regimes are very carefully discussed both from experimental and theoretical part in this nice book, Semiconductors and Semi-Metals, and there is a special chapter called Exciton Diffusion in Two-Dimensional van der Waals Semiconductors, and this chapter is written by Alexei Chernikov, who is involved in experiment, and by Mikhail Glazov, who is performing theoretical calculations. So let me now show our original results, and we are interested, when I will speak about diffusive regime, we are interested in the special situation when there are two subsystems of excitons in the system. So it can be called fast or slow excitons, or moving or wrapped excitons, and there are some experimental realizations when such situation could appear. For example, the presence of localized states can be well understood from the analysis of photoluminescence of the system, and in addition to the peak which corresponds to the exciton recombination, you will have a low energy shoulder which corresponds to the presence of localized states. And in this paper where excitonic transport was analyzed in perovskites, in the layered perovskites, this model was proposed. So we have three propagating excitons, and you have traps, and if exciton is in the trap, it could move. But it could be, and it couldn't be detrapped. And here is the experimental realization of the diffusion coefficient measurements. You can see that the initial time of system evolution after excitation of quasi-particles, you have linear diffusion with a coefficient which is quite small. This is a rather typical coefficient for excitons diffusion. It may be 10 times higher, but not more. And so the diffusion is very slow. It's the speed of a snail. But when the exciton cloud starts to spread, after this linear diffusion regime, localization regime appears, and there is no further spreading of the cloud of excitons. More interesting situation was found in nanoplatelets. So these results in this paper, these results were obtained 10 years earlier. But here the authors demonstrated that not only trapping, but also detrapping processes can appear in the system. So you have freely moving excitons, some of them be trapped, they spend some time in the traps without recombination, and then the trapping appears, and it was demonstrated that photoluminescence in this case is not a multi-exponential function, but there is an exponential decay at the initial time moment, and then it turns to the power law tail, which corresponds to the processes of excitons detrap. So these are the results which demonstrate the presence of two subsystems. Some other possibilities are also possible. It could be bright and dark excitons. One of them spreads faster than other. It could be excitons and electron-hole plasma. Electron-hole plasma is a fast subsystem, excitons slow subsystem, and both in all these cases negative diffusion usually appears, and so the rule is that if you would like to get negative diffusion, effective negative diffusion, you should consider the multi-component system. It's much easier to get the conditions for negative diffusivity than in the single component system. And we analyzed this system. Okay, here are the equations. So we started by analyzing a rather general model, which includes both linear recombination, exciton-exciton interaction, and also we consider the probability density function for trapping times in the traps. But I would like to show you some analytical results. We solved that model using numerical calculations of the Carl method, and I have an additional slide if it's interesting. I have enough time, I can show it and we can discuss. But to solve this problem analytically, we used a more simple model. So two subsystems, fast and slow, or in both subsystem diffusion is possible. Then there is the possibility for transfer in these subsystems with transfer rates. And one of the subsystems demonstrates linear recombination, which gives us photoluminescence signal, which can be measured experimentally. And in such systems, the main problem for those who are performing measurements is that you can measure only one subsystem. You can't measure the subsystem, this so-called trapped, for example, excitons, because when excitons are localized in the traps, they do not recombine, or if they recombine, this doesn't give you some additional signal for photoluminescence. So you always measure only one subsystem, and this gives you the possibility to detect negative diffusivity. Such system can be solved analytically, and you can have very simple expressions for short time spreading and for long time spreading for both subsystems, for fast and slow, and for the whole system. And what is clear from this analysis, that fast subsystem spreads with the diffusion coefficient corresponding to this subsystem, while slow subsystem spreads with the diffusion coefficient, which is the sum of both diffusion coefficients of the subsystems. And that long time spreading, the expression is nearly similar for all the subsystems. You can see that there is some linear dependence on time, and the coefficient is determined by the system parameters, diffusion coefficients of both systems, and the transfer rates between the subsystems. We also performed numerical calculations of the full system of equations, more complicated, to analyze the role of linear recombination and exciton recombination. And what is important that you can observe negative diffusivity in the absence of both linear recombination and exciton recombination. Have a look. Here is the mean square displacement time evolution for free excitons, red line, for trapped excitons, blue line, and for the whole system, yellow line. So what can we see here? Initially, the mean square displacement for free particles grows linearly, and the trapped excitons mean square displacement also grows linearly, as at the initial time moment, all the trapped excitons are produced from the free excitons. At longer times, we see that there is some kind of negative diffusivity for free excitons, but not for trapped and not for the whole system. But as I told earlier, what we can measure only free excitons. So we can measure the presence of the appearance of negative diffusivity. So why it happens? This is a transitional effect in our case, because at longer times, the majority of excitons are trapped, and free excitons population is renewed by the detrapping of trapped excitons from the localized states. This renewal is more effective at the center of the original distribution because the excitons were trapped earlier at this part of the sample. And this is why you can see in the mean square displacement for free excitons this negative diffusivity, the decreasing of mean square displacement with the growth of time. And what is also important that to observe negative diffusion, you should so the following condition should be present. The time scale of getting trapped must be much shorter than the time scale of the detrapping of the released. So here are experimental results in different systems. You can see that mean square displacement at first starts to increase with time, and then there is some time moment when the mean square displacement start to decrease with the growth of time. In different systems, we mostly like this paper because this paper is so they used our model to demonstrate that even in the presence of exciton interaction, negative diffusivity could appear. So I forgot to say that the role of linear recombination is negligible. So red line is without linear recombination and blue line within the presence of linear recombination. So you can see this is nearly the same line. But exciton interaction a little bit make this effect more pronounced. But there is no need to in exciton interaction. This means that you don't need to strongly excite the energy of the excitation pump shouldn't be very large, and don't need a large concentration of excitons to get the negative diffusivity region. We also used the results obtained experimentally in this paper to fit this experiment by our model, and here is the result. And we also demonstrated that some diagram would be organized for such structures. It includes only the diffusion coefficients of all subsystems and the rates of exchange between the subsystems. And you can find the area of parameters where there will be negative diffusivity or there will not be negative diffusivity. So it seems to me that such quite simple expressions will be very useful for those who are involved in experiments to analyze, is it possible to get negative diffusivity in the system. Let me now turn to the hydrodynamic regime. or collective states of excitons in semiconductors, what is important for the possibility to observe hydrodynamic region of excitons in transition metal dehydrogenase mostly is that exciton scattering should prevail over the exciton phonon and exciton defect scattering. So the typical time of exciton scattering should be the smallest parameter in the system. In this case, some collective fluid-like behavior be observed. Let me start from the two experimental papers where ultra-fast exciton fluid was observed. So the first one was done in Singapore in the group of Konstantin Novoselov. They observe ultra-fast exciton fluid flow in atomically thin MOS2 semiconductor at low temperatures and at rather moderate concentrations below the transition. So here is the scheme of their sample. This is the emblem of the university, and they tried to analyze how excitons spread if you excite them here, and then how it spreads in such a structure. They demonstrated that excitons fluids flow over very large distances, something about 60 micrometers. But the problem is that the speed was extremely high. The speed of spreading was about 6% of the speed of light. This is extremely high. It's unbelievable. And there are some problems with these results. And there was a quite active discussion. But they tried to let us believe that everything is okay, and this is exciton spreading with such fast speed. But how to analyze what regime is it? So they tried to perform some theoretical calculations, and they analyzed two possibilities. The first one was the ballistic exciton transport, when the collisions between particles were suppressed, and the only possibility for scattering was collisions with the sample edges. The density, and here is experimental results. These points, their photoluminescence intensity measured at A, B, C, D, and E points. And two calculations. For ballistic simulation, the magenta line, you can see that there is no correspondence. So they decided to use the hydrodynamic equation, the Navier-Stokes equation, but they considered the situation with zero viscosity, so it was an Euler equation. And in their case, it seems that this hydrodynamic exciton transport seems to be quite, and you have to see that they used the experimental parameters and obtained correspondence between experiment and theory. So their idea was that they observed hydrodynamic exciton transport, but again, extremely fast. So it is a little bit unbelievable. And it seems that the answer on the question, what happens in these systems, was given by Mikhail Glazov and Robert Suris in this paper, where they demonstrated that such a layered structure is something like a waveguide, and that ultra-fast exciton transport can be due to the formation of waveguide modes in van der Waals heterostructures, and the radiation of this, what's the secondary radiation. So this is the scheme. You have incident phonon, it scatters, then you have excitons in the channel, this and the excitons recombine, and the photons in the channel spreads very fast. And then again, you have excitons, and the secondary photoluminescence is measured. So the idea is that these experimental results, this is not a hydrodynamic regime of exciton transport, but this is only the secondary photoluminescence due to the radiation transfer by the waveguide modes in van der Waals heterostructures. And one more paper, which I should discuss, also experimental, they demonstrated a quasi-ballistic exciton transport. So their main idea was to create a very narrow channel. Here, previously, the channel is not narrow. The width is about several micrometers. And this paper deals with the experimental technique, which allows to get sub 10 nanometers channel. They formed a quasi-ballistic exciton transport and demonstrated this transport could be over 5 micrometers. This is room temperature, not low temperature as it was previously. And they show that mean square displacement is proportional to the T in the 1.85 power, and the power law equal to 2 means that this is a ballistic transport. So they say that it's not a ballistic transport, but this is a quasi-ballistic transport, as the power law is very close. So this is a super diffusion, fast super diffusion, and these two papers make it possible to analyze the possibility of the hydrodynamic regime appearance in the system. So, and we, together with Mikhail Glazov, decided to analyze the possibility to observe hydrodynamic regime of exciton transport in different transition metal dehalogenase, monolayers and B-layers, and so this should be the case of non-degenerate excitons, but very strong exciton-exciton scattering. So we started from the kinetic equation for the exciton distribution function and obtained the equations which are very analogous to the Navier-Stokes equations of the continuous equation, which includes generation of excitons and recombination of excitons, and also this second equation, which is very close to the Navier-Stokes equation. But the problem is that we should consider the momentum relaxation and the compressibility of the excitons fluid. So the main problem is to calculate viscosity. And if you can calculate viscosity, you can solve these equations and analyze the possibility to observe hydrodynamic range. And we performed calculations of viscosity. We obtained an expression for the key parameters. So you can see that viscosity depends on the concentration of excitons and also on the relaxation time due to the exciton-exciton interaction. And the relaxation time was also calculated. It is, again, depends on the exciton's concentration and the exciton-exciton interaction constant. So in monolayers, the main contribution to the exciton-exciton interaction comes directly from the electron-electron interaction and hole-hole interaction. So this is an exchange interaction between the identical carriers. In bilayers, the key contribution is from the dipole-dipole repulsion of the excitons. Here is the diagram which I showed previously, and here are the estimations of exciton-exciton relaxation time and the exciton phanon relaxation time, which should be slower than exciton-exciton relaxation time, and it appears so for all the dehalogenaids. Typically, it's 10 times smaller, so the regime when exciton-exciton interaction prevails in the system is accessible. So we can also introduce the constant C, which is the ratio between Bose-Einstein condensation temperature, Bose-Einstein condensation in a wide sense. I will some remarks later. And this viscous temperature. So if this parameter is larger than unity, there are only two regimes: diffusive regime and superfluid regime, and there is no possibility to reach hydrodynamic regime. If this parameter is smaller than unity, three regimes can exist in the system. The diffusive regime, so you need rather high temperatures and rather low densities, and in this case, momentum scattering dominates in the system. For superfluid regime, it appears at low temperatures, at high densities, and momentum scattering and exciton-exciton interaction are negligible. And in the intermediate regime, it's very narrow, but it is possible to observe it. So this is viscous hydrodynamic regime. In this intermediate regime, you need not very high at very low temperatures, and the densities also should be very large. And in this case, exciton-exciton interaction dominates in the scattering processes in the system. And here are the results. So you can model the spreading of the exciton cloud area, which is formed by the laser excitation in different regimes. The red line shows the diffusive regime. The blue lines demonstrate hydrodynamic regimes for different ratios between the scattering times. And also you can see the superfluid regime. This is the fastest one, and hydrodynamic regime is faster than the diffusive. So, but it is much slower than the superfluid region. To understand that this is a hydrodynamic regime, it's better to use exciton spreading in the channel. As I showed earlier, it is quite possible to form channels of different width, and the difference will be as shown here in the diffusive region. On the left side and on the right side, you can see spreading, which demonstrate both qualitative and quantitative difference between the diffusive and hydrodynamic regimes. You can see the parabola shape form of the front of the excitons, and this is directly the demonstration of the presence of hydrodynamic regimes. Okay, I have a couple of minutes, and I would like to finish with the problem of condensation of excitons. So first of all, Bose-Einstein condensation is possible in three-dimensional case, and it appears when the distance between the particles is of the order or less than the de Broglie wavelength. And theoretical prediction of the possibility of Bose-Einstein condensation of excitons in bulk semiconductors were made in 1960s, maybe 10 years after the discovery of excitons. Here is the typical picture which demonstrates the fraction of excitons in the ground state as a function of temperature in three-dimensional case. So you can reach the Bose-Einstein condensation in three-dimensional structures. Again, if you want to understand where are excitons, are they condensated or not, you should use and you should analyze optical properties of semiconductors. And there were several attempts to find Bose-Einstein condensation of excitons in three-dimensional systems, and different experimental techniques were used, spectroscopic studies and the detection of luminescence, and also some transport studies to get the superfluidity regime. But the obtained results could be quite discussable, because you can say that this is Bose condensation, or you can use some other ideas to explain the observed results. For example, the narrowing of luminescence line can be interpreted with condensate formation, and the transport data can be described in terms of phone and wind model. So it seems that two-dimensional systems are more interesting to observe such a collective motion of excitons. So exciton condensation in two-dimensional case, Bose-Einstein condensation is prohibited, as yesterday told Andrei Mikhenkov, and but this is correct if your system is very clean and quite large. But it is possible to observe condensation in the situation when you have a trap or potential well or some localization in which you can, which is the situation when the ground state, there is a gap between the ground state and the excited states is present. In this situation, you can see some condensation of excitons, and there are two typically different systems which are used for the observation of such condensation effects. The first one is dipolar excitons in single or double quantum wells, or van der Waals heterostructures, where electrons and holes are well separated in space, and another structure is quantum microcavities, where exciton polaritones are formed. So again, when you were speaking about excitons, it should be better to you should consider the finite lifetime of these quasi-particles, and really it's better to say that superfluidity appears. This is the Berezinski-Kosterlitz-Tauras transition in two-dimensional system, and the superfluidity present. But this wasn't observed in this novel transition metal dehalcogenide systems. So here are the conclusions. So some regimes of exciton transport were discussed, some peculiarities of negative diffusivity, hydrodynamic regime and the possibilities of exciton condensation and superfluidity. The most interesting questions right now are the following. So here I mentioned 4 points. The first one is the exciton transport in planar heterostructures. They are shown here. These are planar heterostructures, and the main problem which is now solved, if you excite exciton in one part of the heterostructure, how it moves to another part. Is it possible to see some interesting effects in this situation? Another idea is the photoconductivity, and the analysis of tryons and thermopolarons, then exciton transport in magnetic structures, where magnons are present, and there is some kind of a magnet wind which can lead to the very fast spreading of excitons. And also hydrodynamics, especially from experimental point of view, as this ultra-fast transport was observed only twice, and this wasn't hydrodynamic regime. So the idea to demonstrate experimentally that hydrodynamic regime is possible also seems to be very interesting. So I come to the end of the talk. Thank you for your attention.
Thank you very much. We have plenty time for questions, please.
Thank you very much for the talk. I want to ask about the last part, the possibility of condensation of excitons. It's very well known that in bulk crystals, excitons don't want to condense. They rather form droplets or whatever, and basically what you need for exciton condensation, you need very high mobility, small effective mass, and I don't know what else. It's probably low temperature of excitonic gas. So there are some criterions. So have you tried to check how far are you from this boundary between the quantum fluid to droplets or whatever, classical?
So I fully agree. We didn't try. I agree that this is not an easy problem. We want to find Bose condensation experimentally, and as I told, all the evidence would be are discussable, and all the results are discussable, and you can say that it is Bose condensation, or you can use some other theories to describe. But we didn't check. So the only thing we did right now is the hydrodynamic regime, and as we know that below the hydrodynamic regime it should be something like superfluidity or the state compensation. So I tried to say a couple of words, but
No, please.
Вопрос чуть-чуть примыкает к предыдущему, но скорее на двойной грамотности. А скажите, пожалуйста, вот Келдыш, Копаев, Козлов, Максимов, они каким-то краем в каких-то пределах касаются того, что в конце говорили? Или это другие системы, другие режимы, другие параметры?
Значит, да, есть теоретически, давайте тогда, так отвечу, что, конечно, теоретические предсказания есть, но экспериментально, уверенно, никто этого не наблюдал. А то, что наблюдалось экспериментально, это можно трактовать так, но можно использовать какие-то более, подходящие модели. Конечно, это теоретически все это начиналось делать еще, не знаю, в 60-е, в 70-е годы. Известные работы. Мы этим не занимались, но вот просто показалось, что нужно хотя бы пару слов про это сказать. Хотя мы этим не занимались, да.
Would you please tell how strongly the exciton interacts with boundaries? Suppose they propagate in a thin channel, and the channel turns. Will they turn as well or annihilate in the turning point? What happens?
Nobody knows. Really, nobody knows, because it's not quite easy to detect. You should detect single photons. You should know that this exciton is, for example, at the boundary of the edge, and you should focus there to get the photoluminescence signal. So, I can show this picture once again. Maybe this experimental paper, the only experimental paper. It seems that, of course, something happens. Of course, they have finite lifetime, and of course they recombine, but how the edges influence I don't know experimental results which can answer correctly on your question. But I think that theoretically it is possible to analyze.
More questions?
Short question. You mentioned also ballistic propagation regime, but on the phase diagram I didn't see it. Could you please tell where there's the phase diagram where different regimes are? No?
So ballistic should be ballistic. So ballistic regime. I think it should be somewhere here in the diffusive part, because it is so-called super diffusive motion. And in this case, the mean square displacement is not proportional to time, but it is proportional to the time and the second power. This is a qualitative diagram. So the idea was to demonstrate that changing the temperature and concentration, you can switch the system between different regimes of exciton propagation. So of course, if you see here are no numbers, concentration of temperature, the temperature could change from 0 to room temperature, and concentration is typically about from 10 to 11 to 10 to 13. But it also always should be below the mode transition.
Oh, thank you. There was no more questions, please.
I have a comment. I still doubt this phase diagram. Normally, Bose-Einstein condensation at 0 temperature is in place not at any concentration. Just this should be either small concentration or large concentration, dependent on the type of interaction of, in this case, excitons.
So I agree. I told just that the lowest concentration here should be 10 to 11. No, maybe 0 is not good. So this is your
then it's fine. Yes,
I agree with this comment. This is maybe a mismatch, because typical concentrations for such structures is 10 to 11, 10 to 13, and per square centimeter. So it should be 10 to 11 here at the left side of the diagram, and 10 to 13 here.
Mm-hmm. Then I'm closer to it. Okay. Excellent.
If there was no more questions, I would like to ask, as to this work of the Novoselov group, what was the so-called mean 3-puff length or in the exciton fluid, and how is it related to the thickness of these channels?
So the channel here is very thick. It's several microns. And the mean 3-puff, I'm not sure that they showed this number. So I just checked this paper maybe 2 hours ago, and there was no numbers concerning the 3-puff.